In this session, I am going to teach you the basics of polynomial systems. More precisely, I am going to give you a very broad and general overview of the theory of polynomial systems, and then I'm going to focus my attention on practical, ad hoc methods for solving polynomial systems in the context of polynomial systems that arise as problems on exams. So the second part will be our practical session for solving polynomial systems. Let us start by defining the notion of a polynomial system. A polynomial system is by definition a collection of one or more simultaneous polynomial equations in one or more variables. For example, a typical one-variable polynomial equation, such as x squared plus 2x minus 3 equals 0, so that would be a polynomial system. Of course, a polynomial system consisting of only one equation with only one variable. The variable is x. Typical polynomial systems would have more than one variable and more than one equation. Here is an example. The first equation is y squared plus xy minus 4y minus 2x plus 4 equals 0. And the second equation is y squared x minus 2y x minus y minus 2x plus 4 equals 0. Notice that when we write polynomial systems, it is usually custom to write a vertical line next to the two equations. So this vertical line indicates that the two equations are taken simultaneously together. So that indicates the fact that we're speaking of a polynomial system. Okay, so we said that this polynomial system has more than one variable and more than one equation. How many variables do you see and how many equations do you see? Well, I'm sure you saw two equations and you hopefully saw also two variables, namely the variables x and y. The number of variables in equations need not be equal. For example, we could have the following system: x plus y plus z plus w equals 2, y plus z squared equals 1, and y plus zw squared equals 1. This system would have four variables, I'm sure you guessed it correctly, but it only has three equations. So the variables would be x, y, z, and w, and the equations are only three. So it is possible to have that the number of variables is different from the number of equations. It is also possible to have it the other way around. It is possible to have more equations than we have variables. Polynomial systems may fail to have solutions. For example, let's look at this system. The system of two polynomial equations. The first one is x equals 0, and the second polynomial equation is x times y equals 1. Now the first equation clearly implies that x is equal to 0, but then the left hand side of the second equation is 0 times y, and 0 times y is always equal to 0. So no matter what we choose for y, we can never satisfy the second equation. So the second equation will never be solved. So that polynomial system would fail to have any solutions. Polynomial systems may have finitely many solutions. For example, here's a system with only one solution: x equals 0 and y plus x equals 1. Let's check that that system has only one solution. The first equation again implies that x is equal to 0. The first equation simply says that x is equal to 0. And then in the second equation, if you were to replace x with 0, we get y equals 1. So that is a polynomial system with only one solution. Polynomial systems may have infinitely many solutions. For example, let's take a look at this one. X equals 0 is the first equation, and the second equation is y plus z equals 1. If we set x equal to 0 and y equal to 1 minus z, we produce infinitely many solutions for every possible value of z. So if you were to set y equal to 1 minus z, if I replace y with 1 minus z, z cancels, and I always satisfy the equation y plus z equals 1. So this would be a system that has infinitely many solutions. For every value of z, I can produce one value of x, namely the value x equals 0, and one value of y, namely y equals 1 minus z, which solves my system. The branch of mathematics that studies exact solutions of polynomial systems is called algebraic geometry. Now, algebraic geometry is a very wide branch of mathematics, and the practical aspects of solving polynomial systems are covered under a relatively small sub-branch of algebraic geometry. That is called the subject of elimination theory. So how to practically solve a polynomial systems, that is subject of elimination theory. Solving polynomial systems is an indispensable mathematical tool which can be used in other branches of mathematics as well as directly in the other sciences. There are also some direct applications of polynomial systems. For example, the equations of kinematics. Think of the possible configurations of a robotic arm. So, possible configurations of a robotic arm, those are directly described by a system of polynomial equations. Whether a polynomial system has finitely or infinitely many solutions, what are these solutions? All of these things can be computed with a computer algorithm. In fact, the algorithm can roughly be summarized like this. Find something called a Grobner basis, named after the Austrian mathematician Wolfgang Grobner. Actually, you do that using the Buchberger algorithm. That algorithm is named after the Austrian mathematician Bruno Buchberger, that he was a student of Grobner. And then use the so obtained Grobner basis and techniques from the subject of elimination theory to explicitly find the solutions of your polynomial system. Now, these algorithms are way too advanced to cover here. In fact, the algorithms that I just described would be a specialized course in university, usually studied by math majors. Something more, these computer algorithms for solving polynomial systems are not well suited for pen and paper computations. Such computations can get notoriously large and may even require supercomputers. However, a polynomial system which can be solved by hand would typically be solved in milliseconds on a modern computer. So yes, we can have big problems with the practical aspects of solving polynomial systems, but whenever we have a polynomial system which is difficult on a computer, that polynomial system would usually be intractable by hand. So we would have no idea how to do that by hand. A system doable by hand would typically not require these advanced algorithms. A polynomial system which you can solve by hand would typically be solved easily using ad hoc techniques. That is why, in the remainder of this lecture, we're going to cover such ad hoc techniques. So we will not focus on some general algorithms for which we need computer, because such general algorithms will not be used or expected to be used on a typical math exam. In this example, we're going to solve the polynomial system x minus 4y equals 5 and y squared plus xy equals 10. The first thing we notice is that the first equation here is linear both with respect to x and with respect to y. So this is a linear equation with both respect to x and y. That means that I can express x as a function of y, and I can express y as a function of x, whichever I prefer. Now, you're going to, as you can see, x has a coefficient 1 in front of it, so it makes more sense to express x as a function of y. That will be easier. So I can solve the first equation for x by setting x equal to 5 plus 4y. I'm just taking 4y, the term 4y, and I'm transferring it to the right hand side. When I transfer negative 4y to the right hand side, it becomes plus 4y. Okay, so now I have solved x as a function of y. Next, I have not used the second equation so far, so let me copy the second equation. Y squared plus xy equals 10. Now, I already know from the first equation that x equals 5 plus 4y. So what I can do is I can substitute the variable x away in favor of the variable y. So I can replace the variable x with 5 plus 4y. Once again, we found that x equals 5 plus 4y from the first equation. So now my second equation becomes y squared plus 5 plus 4y times y equals 10. Now this equation is a single variable equation, and we can use techniques from polynomial equations in one variable to solve this final equation. Okay, so first let us distribute 5 plus 4y, the whole thing times y, equals 5y plus 4y squared. We can also transfer 10 from the right hand side to the left hand side. Of course, when 10 is transferred to the left hand side, it acquires a minus. Okay, now let us combine y squared and 4y squared to 5y squared. Now this is a quadratic equation in y. We get the equation 5y squared plus 5y minus 10 equals 0. That quadratic equation can be directly solved. However, before I proceed to solve the quadratic equation, let me notice that all three coefficients, the constant term, the coefficient of the linear term, and the coefficient of the leading term, all these three coefficients are divisible by 5. So let me divide both sides of that polynomial equation by 5. On the right hand side, I get 0 divided by 5, so on the right hand side I get 0, and on the left hand side 5 divided by 5 is 1, and 10 divided by 5 is 2. So I have simplified my equation to the quadratic equation y squared plus y minus 2 equals 0. Now this quadratic equation can easily be solved with a quadratic formula. However, this quadratic equation has an easy factorization, and you can guess that easy factorization with greater ease than using the quadratic formula. So, can you guess a factorization of y squared plus y minus 2 for me? I'm sure you guessed it correct. You get y minus 1 times y plus 2. Once again, how we guessed that factorization, the numbers that we tried here were the numbers plus or minus 2 and the numbers plus or minus 1. So these were the two numbers we tried, and then we quickly uncovered the parentheses in our head to check that the correct factorization is y plus 2 times y minus 1. Our factorization is complete. Next, we get that either y must be equal to negative 2, that we get from the first factor, or y is equal to 1. So our solution branches into two cases. Case 1, y equals negative 2, and case 2, y equals 1. In the first case, well, we are not quite done because we haven't found x yet. However, we remember that x, from the very beginning, we found that x equals 5 plus 4y. So x equals 5 plus 4y, but we just found that y is equal to negative 2. So I can replace y with negative 2 to get that x equals 5 plus 4 times negative 2. In other words, x equals 5 minus 8, and 5 minus 8 is negative 3. So our final answer is x equal to negative 3, y equal to negative 2. This is in one of the cases of the solution. In the other case, y is equal to 1, and again x is equal to 5 plus 4y. So this implies that x equals 5 plus 4 times 1, which implies that x equals 5 plus 4, which is 9. So our solution is complete. Let us collect our results in a final answer. Our final answer is either x is equal to negative 3 and y is equal to negative 2, or x is equal to 9 and y is equal to 1. So we got two pairs of solutions. Now that we have our final answer, let us very quickly check our work. So here's our final answer: x equals negative 3, y equal to negative 2, or x equals 9, y equals to 1. Okay, so let's check the first one. Let's check x equal to negative 3, y equal to negative 2. So what I'm doing is I have copied the first polynomial here, x minus 4y, and the second polynomial there. And now in those two polynomials, I'll carry out the substitutions. X I'm going to replace with negative 3, and y I'm going to replace with negative 2. So I get, on the first line, negative 3 minus 4 times negative 2. And on the second line, I get negative 2 squared plus negative 3 times negative 2. So on the first line, let's see what I get. Negative 3 minus 8. So on the first line, I'm getting negative 3 minus 8. So I'm getting negative 3 plus 8, which is indeed equal to 5. And on this line, I'm getting 4 plus 6. Negative 3 times negative 2 is 6, which is indeed equal to 10. So indeed, I do have that x minus 4y is equal to 5, and y squared plus xy is equal to 10, exactly as was required to solve this system. Similarly, let's check the answer: y equals 1, x equal to 9. So let me replace x with 9, and let me replace y with 1. So what do I get here? I get 9 minus 4 times 1, so I get 9 minus 4, which is equal to 5. Here I'm getting 1 plus 9, which is equal to 10. So indeed, for the second answer, y equals 1, x equals 9, I do get the correct output when I replace x and y with the corresponding values. So this checks my work and completes our problem. In this example, we're going to solve a text problem which reduces to the question of solving a polynomial system. Let me read the problem for you. The sum of two numbers x and y is 25, and the sum of their squares is 330. Given that y is greater than or equal to x, find x and y. Our first step in the solution is to express the text of the problem into a system of polynomial equations. The first thing we notice is that our two numbers are given names, x and y. Second thing we notice is that the sum of x plus y is 25. Next, we notice that the sum of the squares of the two numbers is 330. That means that x squared plus y squared is equal to 330. Once again, we notice that in this polynomial system, one of the equations, the first one, is linear both with respect to x and with respect to y. Whenever we have such a situation, again we can use the trick that we just saw in the preceding example. So we can solve x as a function of y or y as a function of x and use that solution to replace one of the two variables away. So let's do exactly that. Let us solve y as a function of x. So I can take x, transfer it to the right hand side at the cost of a minus, to get that y is equal to 25 minus x. I still haven't used the second equation, so now let me use the fact that y equals 25 minus x in order to eliminate the variable y. So let me replace the variable y with the expression 25 minus x. So I get that x squared plus 25 minus x, the whole thing squared, equals 330. Just as in the preceding example, this is a quadratic equation with respect to the variable x. So, and I know how to solve a quadratic equation in one variable. So, let us simplify first the equation. Just a reminder, we have a formula. A minus b squared equals a squared minus 2ab plus b squared. So that formula can be used to uncover the parentheses here. So 25 minus x, the whole thing squared, equals 25 squared minus 2 times 25 times x plus x squared. Here 25 plays the role of the number a, and x plays the role of the number b. Next, I have taken the number 313 and I have transferred it to the left hand side at the cost of a minus. Next, let me combine like terms. X squared plus x squared equals 2x squared. 2 times 25 equals 50, and 25 squared equals 625. Let us verify that really quickly. 25 times 25 equals, now 5 times 5 is 5, carry over 2, 5 times 2 is 10, plus 2, 12. 2 times 5 is 10, 0, carry over 1, 2 times 2 is 4, plus 1 is 5. Add the two together, 5, 2, 6, 625. So 25 squared is equal to 625. Next, 625 minus 313 equals 312. Okay, now we have obtained our quadratic equation with respect to x, and we know how to solve. Before we solve this quadratic equation, however, let us notice that all coefficients in that equation are divisible by 2. So to simplify our work, we're going to divide this equation by 2. On the right hand side, 0 divided by 2 remains 0, and on the left hand side we get x squared minus 25x plus 312 divided by 2. 312 divided by 2 is 156, right? So 156 times 2 is 100. So 156 times 2 is equal to 2 times 150 plus 2 times 6. So that's equal to 300 plus 12. So that is 312. So 312 divided by 2 is equal to 156. Alright. So now we can try to guess the solutions of this quadratic equation by factoring. So I could now factor this quadratic equation with respect to x. However, this particular quadratic is not so easy to factor. Why? Because 156 has many divisors. So many divisors. Many divisors of 156. Now, if you so desire, I challenge you to try to guess a polynomial factorization of x squared minus 25x plus 156. Feel free to pause the video and try to factor that polynomial, but I will not actually factor the polynomial. I will directly use the quadratic formula to solve this quadratic. Once again, the reason I'm using directly the quadratic formula is because perhaps this polynomial is a little bit on the large side, the coefficients are a little bit large, and this polynomial may be a little bit difficult to factor easily. So I'm simply going to use the quadratic formula. So my two roots of my quadratic equation are minus b is negative 25, plus or minus radical of 4 times a, the coefficient a equals 1, times c, the coefficient c equals 156. So this is the coefficient b here. We're actually having negative 25 squared, but negative something squared is just equal to that thing squared. So negative 25 is our coefficient b. Okay, so here once again, here I had written 25 squared, but that's in fact the same thing as negative 25, the whole thing squared. So here's what I'm getting. So minus 25 is plus 25. 25 squared, well, we already computed that 25 squared is equal to 625. And 4 times 156, well, 4 times 150 equals 600. 4 times 6 equals 24. So altogether 4 times 156 equals 624. Once again, 4 times 156 is equal to 4 times 150 plus 4 times 6, which equals 4 times 15 is 60, so that equals 600, and 4 times 6 is 24, so altogether we get 624. Okay, so we get 25 plus or minus radical of 625 minus 624 over 2, and 625 minus 624 simplifies to 1. That was an easy one, and in fact we are having a radical of 1, but radical of 1 is of course this, equal to 1. So we get 25 plus or minus 1 over 2. So we get either 25 plus 1 over 2 or 25 minus 1 over 2. So finally we get 26. We get 26 halves, which equals 13, or we get 24 halves, which equals 12. So our two solutions are x equal to 13 and x equal to 12. So I'm running a little bit out of space in here, so I'm going to take these formulas and I'm going to move them up. So I'm going to hide part of the preceding computations and I'm going to move the highlighted formulas up. When solving a problem by pen and paper, you can simply turn to the next page. Please be very careful when copying expressions from one page to another. Okay, so now we have our two solutions for x equal to 13 and x equal to 12. Now, we haven't found y yet, so let's take care of that. Y equals 25 minus x. So y equals either 25 minus 13 or 25 minus 12, right? Because x is equal to either 13 or 12, which means that I have to replace x with either 13 or 12. So I get that y is equal to either 12 or 13, but in the opposite order. So when x is 13, y is 12, and when x is 12, y is 13. Notice something interesting. Our solutions appear to be symmetric with respect to y and x. So our first solution is x equal to 12, y equal to 13, and our second solution is x equal to 13, y equal to 12. Now this symmetry is to be expected because notice that this first equation, x plus y equal to 25, is symmetric with respect to x and y. If you swap the values of x and y, you still satisfy that equation. Second equation has the same property. If you swap the value of x with the value of y, you still get the same quantity for x squared plus y squared. So we knew that our solutions must be symmetric. So if 13, 12 is a solution, then 12, 13 must be a solution to our system as well. Okay, so here are our two solutions candidates, but are both of those solutions allowed? Have we used everything that was given in our problem? Well, not really. We were given some extra information. We were given that y must be greater than or equal to x. So since y is greater than or equal to x, one of these two solutions needs to be discarded. Right? So this solution here is to be discarded because for this solution x is greater than y rather than the other way around. So the only remaining solution is x equal to 12, y equal to 30. And that is our final answer.